Hello grade 12s, welcome to Learn Extra. Today we're going to be looking at Euclidean geometry, and in particular we're looking at the conditions for a polygons to be similar, and secondly to use similarity theorems to solve riders. So let's go now and have a look at these theorems and discuss how we go about them. Right, so if we talk with similar polygons, first of all we need to talk about what is a polygon. Now poly means many, and so it means a many-sided figure. In actual fact, you're probably mostly going to see triangles, but there's no rule that says that has to be the case. So basically it's saying it's closed shapes in which the corresponding angles are equal and the corresponding sides are in the same proportion. So if it is say a figure like this, for example, like a kind of pentagon, that would be a polygon, and perhaps a smaller version of it. What they're doing is they're saying, if say that angle equals this angle, that one equals that one equals that one, this one equals this one, and say this equals this. So that would be a closed shape in which the corresponding angles, corresponding means in the same position, are equal, then the corresponding sides are in the same proportion. So they're telling me that this side will be proportional to that side. So the ratio of that to that is equal to the ratio of that to that, etc., etc. Now, as I say, in actual fact, it's more likely you're going to work with triangles, but there's no rule. It said polygons in the actual statement. So yes, it could be more than a triangle. Let's go on. Nothing much changes. Then they talk about congruent polygons. Now, congruent, you'll remember from earlier years, means that it is absolutely identical. So if I was doing this here, it would be a complete clone of, say, this one with this one. So there would be two identical shapes. So if I chopped it out and pasted it on top here, it would fall exactly the same. So they are identical in terms of angles and in terms of sides. So the one has got a constant ratio to the sides, and that's the similarity, and the congruency is exactly the same. So they are, if you like, 1 to 1. So in other words, 1 to 1 would mean that they are exactly the same size. Let's have a look at the theorem. Okay, it says here similar polygons have the same shape but are not the same size. That is what we've been discussing. If triangle ABC is similar, that sign over there that I've just put in there means similar to triangle DEF if it means that angle A equals angle D. So let's get the drawing up so we can refer to it. So angle A equals angle D, angle B equals angle E, and angle C equals angle F. So you see how I'm saying these are corresponding angles are equal positioning wise. Then we can say that the ratio of this side to this side. Now if you look at it, that is the side containing that little half moon and the cross, the half moon and the cross. And let's change the color pen so we can look at the next one, and the next one is going to be BC. That isn't a good color for the screen, so let's choose this one. Or even worse, so let's go to green. BC to EF, and then one more color change, AC to DF. So for example, if this was say 3 and this was 6, if this was 2, what did I do here? Well, 3 to 6 is in the ratio 1 is to 2, so this would have to be 4 to get the same ratio. And over here, if this was 1, this would have to be 2, because this one is double the size of this one. It needn't be double, it could be treble, whatever you want it to. It's not important. Okay, so that is what the theorem is saying. Let's just take the values off here. I don't want to really have them interfere, but I want to spend a few seconds mentioning something more about this story. Now, when we actually work with this similarity, let me just get a pen up here. When we work with this similarity, we actually have to be very careful how we set it out. So what we would do is we'd always start by saying in triangle ABC and triangle DEF. Now over here, it doesn't matter about the order I'm putting it in. It becomes important at the end when I introduce that little sign that we've got up here, this one over here. Then it's important what the order is. So over here now, what I would do is I would outline at least two angles that are equal. Now they've told me that A equals D. So I can go A equals D. A equals D. Now I just want to say here, notice that I'm keeping the details of triangle ABC under ABC and the details of DEF under DEF. So there we go, we got that. Then they told me that, and that was given, so we can write that down. Then they told me that B equals E. So B equals E, and again it was given. Now what is beautiful about working with a triangle is that once you've got two angles equal to two angles in another triangle, the third must automatically be equal. In this case they've told me because it's the actual theorem, so it's not a problem. But you can remember always that the third angle is a result of the angles adding up to 180. So what I could have done is I could have said yes, and angle C equals angle F, and I could have written a third angle of triangle. But in this case, they told me it was given, so I could have just kept to that. Now, what I wanted to do this for is to remind you about something that's going to make your life incredibly easy. If you have listed your triangle ABC under ABC and your triangle DEF under DEF, you now can do something very useful. You can say triangle and you can list them in the order you've proved them. So ABC is similar to triangle DEF, and the reason would be equiangular triangles, or you can just use angle, angle, angle. I'm sure you remember your grade 9 teacher telling you that that's not a condition for congruency, and of course he or she was quite right, it's not. It's a condition for similarity. Now once we're here, we can see that this A is the same size as that D, and they're positioned in exactly the same place. B is the same size as E, and they're both positioned in the same place. And C is the same size as F, and they're positioned in the same place. Now, if this is how you've got it, it makes your life a little bit easier. Let's just erase that, and then I'm going to show you how you can get those ratios really easily once you're in that position. So now what we can do is we can take the first two, which is A, B, over the first two of these, which is DE. And we can say that is equal to the last two over the last two. So we can say BC over EF. And then we can take the first and last and the first and last. So it's going to be AC over DF. Now, if we go back to our drawing, we'll see that that fits in perfectly with what we said just now. If you look back to the drawing, remember what I said to you, we put these sides that are proportional together. So if we look over here, AB to DE, the half moon and the cross, half moon and the cross. BC to EF, it's this blank angle which I'm going to put a circle in with a cross, the blank angle and the cross. So there we have it. And the last one is AC to DF, which again is the half moon with a circle, half moon with a circle, and so we've got it. And this is the actual theorem. It says that if the angles are equiangular, the sides are proportional. Now there is the converse of this theorem, which says if we have those ratios the same, then the angles are equal. Now I want to just quickly draw it because I'm a great believer that geometry is best taught in picture form. It makes more sense to you because you're going to look at your rider, or your problem as we call them riders. We're going to look at it and we're going to see it as a picture. We're not seeing it as words. So learning words doesn't help you necessarily when you're looking at your drawing. So let's go have a look at what I'm meaning by that. So what I'm thinking is, if I was going to make sense of this, I'd say, right, I've got two little triangles, whatever they might be. Let's keep to the numbers, the letters we've been using. And the theorem says if B equals E, A equals D, and C equals F, then AB over DE is in the same proportion as AC over DF, which is equal to BC over EF. Now the converse will say, if this ratio is constant with these sides, it would imply that the angles are equal. So that's quite a useful result to know. So we can work either way, but there's one other thing I've got to mention. It's the actual proportion theorem. Now, before we even start talking about proportion, if I give you a line like this and I say this is AB, and I stick a point in here C, and I tell you that AC to BC is in the ratio 2:1. I want to ask you, does that mean that our AC is 2 units or 2 centimeters or 2 whatever long and the other one's 1? And the answer I'm hopefully you thinking right now is no, it doesn't. Because who's to say that wasn't 20 and 10 and I cancelled it down? Or maybe it was, let's make it 15 and 7.5. All of those would come to the ratio 2:1. So when the ratio is 2:1, we've got to remember it's a ratio and not a length. So one of the things I do to make my life a lot easier is I use a variable, because a variable means it can be absolutely anything. So I would say the length of AC is 2A units, where the A represents anything. So maybe it's a 10, maybe it's a 5, whatever, doesn't really matter. And then this would be A. So if we go back over here and we talk about AC to BC, and using this variable system, we would be able to say 2A over A, which then the A's would divide into each other, and we would get the ratio 2:1. This is very useful, and it saves you a lot of trouble rather than working with the ratio to work with the length with a variable in it. Right, now what I wanted to mention to you is this theorem that, if you like, is a sort of subsection of the similarity theorem. What it says is, if I have a triangle ABC and I draw myself a parallel line anywhere on this drawing, so let's put it over here and let's call it DE, then the sides are divided proportionally. So I'm saying to you that this line, this parallel line, wherever it might be, will result in the AD being proportional to the DB, the AE proportional to the EC. So that's one option. So we could say AD over DB equals AE over EC. We can also say AD, which is this one, to AB, the whole length, equals AE to AC. Notice, short, long, short, long. So we're working with proportion, and you could actually think of it in this way. You could say to yourself, I know that that angle equals that angle because those angles are corresponding angles. That one equals that one because it's corresponding. And this one, of course, is a shared angle between triangle ADE and triangle ABC. So we have those three angles like I've just mentioned to you, which means they would be similar, which means this ratio would apply. And of course we can take any variation of that similarity and it'll work. So let's go to our first problem. Here we have it. And what I want you to do is to think in pictures. So looking at that already, I'm thinking about this one I've just mentioned to you, where I had a line parallel like that. And I can see two possible alternatives. Let's highlight the one. The one would be to use this triangle over here. And the other option would be to use this triangle over here. Now, a very good thing when you're doing geometry is to use color, because it helps pull out what you know and you don't know. So let's read on with the question. It says, in the diagram, SB is parallel to RC, which we knew because they had the parallel lines marked in. They tell me that PA to AR. So PA, in fact, I think I'm just going to undo this or rub out this color, just so we can put the values in, and we'll come back to the color later on, because I think it'll just make it easier to not have the drawing looking too messy at this stage. So PA to AR. PA to AR is in the ratio 6:5. So remember when I said to you, now we can't say that this is 6 units long and that's 5 units long. So we place hold by saying 6A and 5A. Then they tell me that PB to BQ. So PB to BQ, this guy here, is in the ratio 3:7. So I'm going to call this 3B and this one 7B. And then they actually give me a length. They tell me, let's just get a purple up here, that PQ, this whole length, is 10 units long. And again, I didn't do a very good job of writing my 10, so let's just write it again. 10 units long. Now that is an actual length. Now I'm sure you can see how nice that is, because if we look over here, we know that 3B plus 7B has to equal 10 exactly. They've told me that, which means 10B is equal to B, which means B is equal to 1. So that's very good news, because now I can go to this one, and instead of going 7B, I can write 7, and instead of going 3B, I can write 3. Okay, and that makes sense to me now, because I knew the whole length. If they said this whole length was 20, well then I would have written a 6 there and a 14 there. But fortunately for us, it was a nice easy one. We knew that B was equal to 1. Okay, so I've written some stuff on the drawing. Let's see what the actual question's asking. It says, calculate with reasons the value of BC. So let's go back to the drawing. We want the value of BC. That little line there. Now remember what I said to you, we can be looking at two different triangles. Now for this one, I can safely say we're looking at triangle PCR. So let's just erase this here so we've got some room to work. Now I would suggest this is how you set it out. So we would say, in triangle PCR, we know that BA is parallel to RC. It was given. Okay, so we know that this line is parallel to that line. Remembering we're trying to find this one over here. I'm going to put a question mark on it. And if we look at it, we can see that the ratio would exist that PB to BC is equal to PA to AR. Now, what I would suggest you do is, since we want to find BC, we would start with BC at the top of the fraction. So we'd say BC over PB. So I've taken the bottom one between the two parallel lines over this one. So here I must take AR over PA, because that would be proportional sides between the parallel lines and above the parallel line, between the parallel sides and above the parallel line. So now that would be line proportional parallel, to one side of triangle. That would be the reason we would use for this particular statement. You could also use similar triangles if you like, but I think it's easier because you would have had to say which triangles are similar if you did that. So right, that means BC we have found, this is what we need to find. PB we have found to be exactly 3 units. AR was 5A and PA was 6A. See, the A there does nothing serious because we can say that A divides out and we're back to our ratio. So our BC is equal to 5 over 6 times 3 over 1. And that goes into there twice and into there once. And so we can say BC is 5 over 2, or if you like, you could say 2,5. It's up to you. I personally like a fraction, but it really doesn't matter if you decide to work with a decimal. Right, so now let's go to the second one, and I've decided to go to a clean drawing so we've got lots of room to maneuver. So let's go back to the drawing and just fill in what we know. We've just found this to be 2,5. We know that this whole distance was 7, this distance was 3, and we knew that this was 6A to 5A. Right, so now we're going back to the second question, as I say, and the second question says QS over RS. So let's highlight that. Let's take another color pen. So we want QS to to RS. Now, I think you can see clearly that if we're using these parallel lines, we are working with this triangle here to get that ratio. Now, remember what I said to you? I suggested that you write down which triangle you're in. So you tell your examiner, in triangle QBS. And a very good idea is also to tell them which parallel lines you're working with. So you can say BS parallel to RC. And now we can start the question. Now we have to have the same proportion. We want QS to RS. So it's the whole side to the little one between the parallel lines. So the matching one would be the whole side to the little one between the parallel lines. So it's going to be Q, I think it was a B. Let me just make sure I'm not telling you nonsense. Yes, it is a B. Okay. QB is to BC, and it would be line parallel to one side of triangle. Okay, and now we can go QS to RS equals. Now, is it any problem getting us QB? No, we know QB is 7. And we know that BC is 2, 5. And to be honest, I would prefer to work with it as 5/2. But you're welcome to use the decimal as I've explained. So that would mean that is equal to 7 times, and of course we're dividing by a fraction, so we invert and multiply. So we get 14/5. And that'll bring us to the end of the question. We've got the ratio of QS to RS. And if we were going to put it in just for matter of interest, it's not what they asked me, I could go 14C to 5C if we wanted to do that. But it's not necessary within the context of this question. Right, let's look at the next question. Okay, example 2, here we have it. Let's take up the drawing. And again, if you look at that drawing, I'm sure you're seeing those parallel lines staring at you and shouting, here I am, here I am. So let's highlight them. We can see clearly that this one is parallel to this one, which means that triangle becomes a very strong option to use that little result we've just been working with. And this one parallel to this one. Now, it's not a bad idea, as I said, to use color, highlight up your parallel lines. It makes it easier for you to start the question. Notice I haven't even engaged with the question, but I've made sure that foremost in my mind is those parallel lines. So let's go down to the actual question. It says, in figure ADBHCG, that's enough to scare the best of us. But don't worry, all they're doing is they're naming all the aspects of the actual figure. DE is parallel to BH, FG is parallel to EC, and then there's one extra point here. F is the midpoint of line segment AE. So we've got those parallel lines in place. F is the midpoint of that, so we know that that's equal to that. And you know, you can highlight, but I think it's easier to just show the two little markings that are the same, and then you will remember that that's the case. Of course, that should make you think back. I think it's in grade 10 where you talk about the midpoint theorem, which is a special case of these theorems we're doing today. So if you're remembering that, you would remember that it says if FG is parallel to EC and AF is equal to FE, then AG equals GC. But let's carry on with the question and see what else they're asking me. Now, it is further given that AD to DB is 2 is to 3. So AD to DB is 2 is to 3. So AD to DB is 2 to 3. Now remember, that's a ratio. So to make sure I don't get into trouble, I'm going to call this 2A, and I'm going to call this one 3A. That way I sort of placeholder it, and there's no real problem with it. Right, let's go down and see what else we've got here. Now they asked me to find DE to BH. Okay, DE to BH. Right, so let's highlight what we're looking for. DE to BH is in fact the two parallel lines. Now you might have remembered when I was doing that, I never used the parallel lines, but I did say to you it's a special case of similarity. So what I'm going to do is I'm going to prove triangle ADE and triangle ABH similar, because then I can actually work with the parallel lines themselves. Now remember what I said to you, I said we have to have at least two angles equal, the third is automatic. Right, so if we look over here, the easiest one to spot immediately is that this angle equals this angle. So I could say angle D equals angle B. The reason is it's corresponding angles. Now just remember, you must say which lines are parallel, because corresponding angles are not equal unless the lines are parallel. And then we could say this angle and this angle, so we can say E is equal to H, also corresponding angles, same parallel lines. And then the third angle, remember, is automatic, but the third angle is the shared angle. So A equals A, and I'm actually going to put their common angle. You could write third angle of triangle. Therefore, triangle, and remember what I said to you is if we've been careful and we've put our facts underneath the right triangles, we can actually take our order straight off our work. So we can go DEA is similar to triangle BHA. And just to stress the point again, we may not use this symbol here unless the angles are positioned in the same position in the thing when they are equal. So I know that D must equal B, E must equal H, and A must equal A. Right, so now I can use that shortcut I showed you. So I can say the first two over the first two equals the last two over the last two equals the first one and the last one over the first one and the last one. Right, so now we're in a position to actually see what we've got. So what I normally do is I now look at this picture and I say, right, I'm looking for DE, so I want to have that one in. I'm looking for BH, I want that one in. EA, I know nothing about except for the fact that it's divided in half by F. And HA, I know nothing about at this moment, so I can erase that one for now. But DA, I know is 2A, and BA, I know I can find in terms of A. So those are the ratios I've got to work with. So what I would do is I'd take the three, I'd tick what I needed, and then I would isolate them. So I'd say, all right, well, I want DE over BH is actually what I want. And DA, we said, was 2A. And BA is this entire length, so it's going to be 5A. So we have DE over BH is 2 over 5, because the A's will cancel out. Now, that's a good result to remember, so I'm going to keep it up here, because probably, in all likelihood, the next one will require me to use that. Another way to do it is to go straight to the drawing and fill it in. So let's do that as well. So what I would do is I'd say, okay, my green lines, I can call this 2B, and I can call this 5B. Might be useful later on, so we do that. All right, let's go on and see what they wanted me to do next. Next, they wanted AG to AC. So AG to AC. So AG is this guy, and AC is this whole one. Will we still be working with the same parallel line we were working with before, where we can see that those green parallel lines have got nothing to do with those two sides? So in actual fact, we must be working with the pink parallel lines. Now, the good news is this is not these sides, the actual parallel lines, they're the sides, so that means we can use the shortcut. So let's quickly erase this work we've got over here. Let's just pick up the razor, get rid of it. Okay, and then we can go back to our pen. So right, so now remember what I said to you, if we're going to use that one, a good idea is to tell them what triangle we're working in. So it's in triangle AEC. We know that FG is parallel to EC. Now, if that is so, well, we don't have a problem because we know that AF, let's start with the one we wanted. We wanted AG to AC. So AG is this one, so the matching one would be AF, and AC is the entire length, so the matching one would be AE. Now those are equal, and the reason would be line parallel to one side of the triangle. Right, so once we're here now, it's just a matter of tidying up. We know that F is the midpoint. So do you agree with me? I could go AF, and instead of AE, I could say twice AF is equal to AG over AC. The AF divides into the AF, and so we have the result that a half is equal to AG over AC. So a half is equal to that, so we could call this, and you might notice it's getting quite interesting on this drawing, but it doesn't matter, it's quite useful. C is to 2C because you never know if you're going to need it. So over here we're going to go and we're going to say a half. So that result is one of the ones we have. Let's see what else they asked me. They now ask me for FE to EH. FE to EH. Right, let's just get some space here. Right, we've got plenty of room there. And let's just change the color of our pen so it's clear we're not working with the same things. So we want FE, this guy, to EH, this one here. Okay, now that's quite an interesting thought, because if you look at that, that's not part of a triangle with a parallel line. But we do know that we can find something about AE to EH, because with that green parallel line we can get somewhere. So I'm going to say in triangle ABH, I know that DE is parallel to BH, and because of that I can say AD over BD is equal to AE over EH. Now AD was 2A, BD is 3A, and so we know that AE to EH is the same, so it's also 2 to 3. Now if that is so, I'm saying to you that this here is 2D to this being 3D. But I know that F is the midpoint, so if that's 2D, this will be D and this will be D. So therefore AF is equal to FE, okay, and therefore we can say that's from the fact that we were given that, and therefore we can say that the one we wanted, which was FE, would just be D, and the other one, EH, is 3D. So we can say the answer is 1 is to 3. 1 is to 3. So the drawing is starting to look a little bit like a colouring in book, but it's fine, not a problem, because I'm sure there's a reason why we're getting all these results out. Let's look at the last part of the question. The last part of the question asks you to find the area of that over the area of the other one. Now before we move on, if we're going to find the area of a triangle, we have two ways of doing it. The first way is to know the perpendicular height. Question, if we go back to this drawing, do we know any perpendicular heights? And hopefully you can all see that that is not so. So if that's not so, we have to use the only other way, which is area rule, which you learned last year. So let's just clear this little space up for us, and then we can start. Right, let's go down and see which it is. I'm pretty sure it's the two overlapping each other, but let me just make sure. Area of ADE and ABH. Area ADE over the area of ABH, I think it was. Let's just get the drawing next to us so we can see. Yes. Now, it's a very common question, this, and it's a lovely little question because you can rest assured that there will be a shared angle. And so when you use your sine rule, if it's not shared, I mean not just sine rule, your area rule, if it's not shared, it must be an angle that's equal. In this case, the good news is it is shared. This angle A belongs to ADE and it belongs to ABH. So if we're using our area rule, it is half the product of the two sides. So in this case, it would be AD times AB, the sine of angle A. And underneath, we would have a half of I think it's AH. Let me just make sure I'm not giving you the wrong details. AB, sorry. AB times AH, the sine of angle A. Now that's good news because if we go back to that, we can see that the halves will divide out and the sine A's will divide out. So we're left with AD times AB over I think it's AE. Sorry, my handwriting leaves a lot to be desired sometimes. That was an E if I did a very bad job of writing an E. So that was AE, and this is AE. And this is AB, AH. Right, so if we look at the drawing, we already know those values in terms of A's and B's, which will help. AD we know is 2A. AE we know is 2D. AB is 5A. And AH is 5D. So those D's there are not going to cause any problem. They're going to cancel out, nor the A's, they're going to cancel out. And so we're left with 4 over 25. Isn't that a beautiful little question? It really shows such nice thinking. And it's also, you know, teachers love asking questions that have integration of sections. So you've got a bit of sine, an area rule in the middle of a geometry question, which is just lovely. Okay, let's go to question 3. In the diagram below, O is the center of the circle with diameter RK. PS is perpendicular to RK. So let's fill in what we know on the drawing. They're telling me O is the center. I think they've made it clear. They've told me RK is the diameter. And they've told me that PS is perpendicular, and it's marked in beautifully for me, so I don't have to worry. Then they tell me RK intersects PS at T. So that's fine. That's all marked in on the drawing. So we've got very little to worry about here. Now, hopefully, as you're looking at this question, you are thinking back to your grade 11 theorems. And there's one in particular that is just screaming at me here. And the one that I'm thinking of is this one where it says, if I have a circle and I draw a line from the center perpendicular to a chord, then it bisects the chord in half. So already I know that this will equal this. Now that could be very useful for me just now. I'm filling it in because while the drawing is clear and it's easy to see what's going on, it actually makes my life a little bit easier. So just remember, always think in picture form, and then you always will see things that you normally won't see other times. Right, now they tell me PS is 4x. Now that's quite good news because with what I know, I can say ST equals TP, and the reason is line from center perp to chord, or whatever reason you've been shown, it's fine. And therefore, ST equals TP equals 2x, since PS is 4x. So it's 2x and 2x. Right, write down the length of ST in terms of x. Well, you've done it. I didn't even think about it. I didn't even look at what the question said, and I've already got it. I know that ST is 2x. So you see, by looking at my drawing and looking for the theorems within the drawing, it just makes it easier for me to actually get into the question. Right, so that's the first part done. Let's see what the second part asks. it says it's further given that RST is similar to PKT, and it's further given that TK equals X and RT equals 320 millimeters. Calculate the value of X. Now that's lovely. We need to fill in some stuff on this drawing before we go anywhere. So let me just erase what we had here. I can leave the 2X's in because we needed that. And let's get ourselves another color and let's go looking for what they told me again. Right, it's given that triangle RST is similar to PKT. Now remember what I said to you when we started? I said that means that angle R must equal angle P. Let's just look at the drawing and see if we can see it. Yes, R equals P makes perfect sense. I don't think we need it, but I'm just going to put it in. S equals K, so S equals K, which we know as well from our theorems from last year. And of course, T equals T, where that's the right angle over there, vertically opposite angles. So yes, it makes sense what they're telling me. Let's read on. It is further given that TK is X, so we know that this distance is X. And they tell me RT is 320 millimeters. So RT, this whole length, is 320 millimeters. I suppose we should put the units in as well to be good. Anything else we're given? Calculate the value of X. Now, why are they telling me those triangles are similar? Well, they want me to use some kind of ratio, obviously. So let's write the ratios up. Remember, the first two over the first two. The last two over the last two. The first and last over the first and last. And we're now ready to go. So do we know RS? No. Do we know PK? No. Do we know ST? Yes, we do. It's 2x. Do we know KT? Yes, it's x. Do we know RT? Yes, we do. And do we know PT? Yes, we do. So this part of the ratio is not needed. So now we go back. ST was 2x. KT was just x. RT was 320. And PT was 2x. Now remember, the instruction was to solve for x. Well, we can see that that x divides into that x. So we have 2 equals 320 over 2x. And by the way, the reason here would be similar triangles or angle, angle, angle. That's what's happening over here. And then as a result, the proportions happen. So now we can say that 4x is equal to 320, which means x is equal to 80. Have we solved the question? Yes, we have. We know that x is 80 millimeters, which means, of course, we know all of these lengths here as well. Right, let's move on and go down, and that's it. That's all we were asked to do. Okay, so very nice little question, but you see, they did help you, but they could have, of course, got you to prove that similarity as well, which would have been fine. Right, let's go to the next one. Right, example 4. In the diagram below, ABC is a right-angled triangle with C equal to 90 degrees and E 2. So I see the 2's missing here, so let's just write it in, equal to 90 degrees. Complete this. Now, this is actually a very nice theorem. Well, it's actually one of the ways we have to prove Pythagoras' theorem, which is ultimately what we're going to end up with here. Now, what they want you to do in this case is to be able to look at the drawing and see which angles will correspond in size. So what I would do is I'd look at it and I'd say ACE. Well, if I'm looking with this little triangle here, not a bad idea would be to use this big triangle, because at least I've got something going. So then the A would be in the shared position, and C, I'm not hesitant to use. E, I'm not hesitant to use because I know that E1 was 90 degrees. And so I can safely say that the equivalent one for E was C. And so the remaining angle in this little triangle over here is B. So in other words, what I've established is that C1 equals B. Now I've got the big one, which is great. So now I'm going to move into this little one over here and try and place it in a similar position. So let's have a look. Well, angle A in the big triangle is not shared anymore, but angle B is shared. So we can put B in the middle section. The right angle, which was the last angle I named, is actually E. And now it's quite easy. I've got E and B, so missing is C. So then I've completed which angles are similar. Now they asked me to show this. Now, as soon as you see squares, it means that you have to use two triangles that contain that side twice. So you look over here, you want AC. So this triangle's got an AC, and this triangle's got an AC. So that would be where I would start. So I would say using these two triangles and knowing that I placed them in the correct order, I can draw up my similarities. So let's do it. We can say AC over AB, first two over first two, is first and last, which is AE, over AC, which is last two ACE over last two BC. But we want AC squared, so we want the AC to happen twice. We want the AB and we want the AE, so this is the part that I don't need. So therefore, if I now cross multiply these, I'm going to get AC squared equals AE times AB, which is that result. And we had the problem solved. Now remember what I said to you? We look again for the next one for two triangles that contain BC. So let's swap our pen. We want BC, there's a BC there and there's a BC there. So it looks like we're going to be using those two triangles. So if we do that, the first two is AB over BC. The next is AC over CE, which is equal to BC over BE. What I want BC squared. I want EB or BE, and I want AB, so that's the ratio I don't need. So if I cross multiply that, I'm going to get BC squared equals EB times AB, which is this result. So that's really nice. We've got that organized and ready to go. And now all we have to do is it says hence or otherwise prove the theorem of Pythagoras. Now, hence or otherwise, I used to have a friend who joked about it. He used to say, hence or otherwise get it wrong. Because really, if they've led you this far, it's really the most sensible way to go and prove it is to use the hence part. So let's go to the top drawing. And what we have now is we have AC squared equals AB times AE. And we have BC squared equal to EB times AB. Right, so now we're going to go to the drawing and we're going to think through the theorem of Pythagoras. Now we've got AC squared as an expression and we've got BC squared as an expression. So we are required to prove that AC squared plus BC squared is equal to AB squared. That's the theorem of Pythagoras. So if we start on the left-hand side, we can replace our AC squared with that expression. So we can say it's AB times AE. And we can replace our BC squared with that expression, and I think I better not use a spotty one. So it's going to be EB times AB. Right, now if we look at that, we can see that AB is a common factor. So let's take it out. So AB comes out, leaving me with AE plus EB. So we're winning a bit because I've got one of the ABs. I need another one. So let's have a look. The other one is AE plus EB. Now if we're adding those, it's in fact AB. So therefore we can say it's equal to AB times AB, which is going to be AB squared, which is the right-hand side, which means we have proved the theorem of Pythagoras. Right, what we're going to do now is have a little break, and we'll be back shortly with some more nice questions to discuss. See you later. Hi, welcome back. I hope you had a good break. Let's now have a quick look at the next question. Let's get going immediately on question 5. Also a lovely little question. There's the drawing. Before I even move on any further, we can see that probably they're going to tell me O is the center of the circle. There's some parallel lines that could be useful, so let's highlight them because we're not going to forget about them, that's for sure. So those could be very useful, so let's keep them there. And let's go and read what it says. So it says there, AOB is the diameter. Now hopefully you remember your theorems from last year, that if you have a diameter, so we draw a diameter like this, what do we know about any angle subtended from the diameter? Subtended just means coming from the diameter. Well, we know that this would be a right angle. Now, if that's a right angle, that's quite useful because it means I can already put that in, and you can see, of course, there's another little factor that happens with those parallel lines. That would be a right angle as well. Now, if that's a right angle, another theorem is springing to mind, the one we were using just now, where we said if a line is drawn and it's perpendicular, it bisects the chord. So I'm going to be able to say AD equals DC. So let's read on and see what else it says. Okay, with O the center, well, that is what we sort of preempted. What I like to do to remind myself it's the center is make it nice and fat. We know that OE is parallel to BC, and they tell me that OE meets AC at D. B and E are joined. Prove that. And the first thing they asked me to prove is that AD equals DC. So you see, without even looking at the questions, I've already orientated my mind towards how I'm going to get this question out. So let's go for it. Let's just clear these away because we've discussed them already. We need to now write this up. And remember, with geometry, you have to tell your marker exactly what you're doing, because you know, everyone does it a slightly different way, and at least if you spell it out for the marker, it makes it easier for them to actually know what to do. So what did we start with? We said angle C is equal to 90 degrees. And the reason for that is angle in a semicircle, or you can say angle subtended at center is twice angle at circumference, but this one is probably better. Then we said that this one here, now notice there's no numbering. Now you usually get given a diagram sheet, so I would number them on the diagram like this. I would say D1 is equal to 90 degrees, and the reason for that is corresponding angles. And remember, you can't just say corresponding angles, you've got to say which lines are parallel, and we know that OE is parallel to BC. So in the light of that, we can now say that AD equals DC, and the reason for that is we can say that a line from the center is perpendicular to the chord. And I think that's what you were asked to prove. Let's just go back and make sure. Yes, AD equals DC. So we've done the first part of the question. Very nice little question, and in actual fact, as I said, if you just use what your drawing's telling you, you've already got that first question. By the way, while we're still talking about this, if for some reason you did not know how to do that first part, whatever you do, don't stop doing your geometry. So then assume it and carry on moving, because maybe the second part and the third part are easy to do with that fact that you've just established. Right, the next part of the question says to me, prove that EB bisects angle ABC. So let's go back up there. BE bisects ABC. So what we're doing is we're required to prove that B1 equals B2. Now I find if you do that, it's just so much easier to work with it. So now what I would do is I'd say, okay, let's find something equal to B1, and let's find something equal to B2, and hopefully that something will be the same thing. So let's have a look at B1. If we look at B1, what is standing out for me is that is the center, which means that length equals that length. And if that is so, then we have an isosceles triangle, so that would be equal. So I could say B1 is equal to E, and the reason for that would be angles opposite equal sides. Okay, some people use the reason isosceles triangle. Strictly speaking, that is a definition, but it's not, you know, we're not out to get you. I think a lot of the departments accept that. Right, so once we're there, we have to get B2. Is there any way that B2 is also equal to E? And the good news is it is. Have a look there. You've got two lines that are parallel. And if you look at B2 and E, they're forming that Z shape of alternate angles. So we can say B2 is equal to E, alternate angles. And again, just like the corresponding, we've also got to say which lines are parallel, because alternate angles are not equal unless the lines are parallel. They are alternate, but they're not equal. They're only equal because of the parallel lines. Right, let's see what the next question asks. The next question says is if OEB is X. So let's go back there. OEB is X. So what I've called a dot, they're calling an X. So let's put it in. In fact, let me just erase all the dots and call them X's. It's just easier to work with the terminology they're giving us. So that's an X, which means that's an X, which means that's an X. Right, let's go back down to the question. Express BAC in terms of X. So let's go back here. BAC, this guy here. Now, I'm sure you can see it's not so bad, because you can see immediately that angle ABC is 2x. That's been proven. And we know that C is 90 degrees. So therefore, what I know about BAC, it must be 180 degrees minus 90 minus 2x. And that's because it's angles in a triangle. And in fact, to help my examiner, I'm going to name the triangle. That is not essential, but it's a good idea. Anything that helps the person marking your paper to understand what you're doing is never wasted. So it's going to be 90 minus 2x. So it's 90 minus 2x. We've answered that question. Right, so that's the end of that question, and you must see it's really a very nice question. It's included some of your grade 11 work, and it's taken your grade 12 into account. So let's move to the next question. Question 6. Refer to the diagram. Diameter AME of a circle with center M. So let's just orientate ourselves. AME, it's clear enough with a circle center M. I think we can see it's clearly a diameter. Bisects FAB. Bisects means cuts in half. So it bisects angle, sorry, I forgot to read it, FAB. F, it's on the bottom, I think. Oops, there's an F missing there. FAB. So in other words, it's doing something to A1 and A2 there. MD is perpendicular to the chord. I think that's clear enough. AB and ED is produced to meet the circle at C, and CB is joined. I think those are all clear enough. Okay, so you can see, look over here. We have our little friend again. Center of the circle, perp to the chord. We know already that that will equal that, but we'll worry about that shortly. I'm sure it's one of the questions. Now it says prove that AEF triangle, AEF is similar to triangle AMD. Okay, so let's have a look. I'm going to highlight these triangles in two different colors so we can focus on them. So it is AEF, which is this guy over here. And AMD, which is this guy here. So to prove similar, we have to find at least two angles equal. And in the light of what they gave me, and I filled it in on the drawing, I already know one of them, so let's put it down. So number one, I know that angle A1 is equal to A2 because it was given to me. So that was simply solved. And now I have to find another thing equal. Well, I can see there's a 90-degree angle over here. Is there a 90-degree angle in this triangle? And hopefully you're remembering the theorem from the previous one where we knew that f was 90 degrees because f is the angle in a semicircle. So let's go back here. Notice I'm not numbering it. I'm saying f is 90 degrees, angle in a semicircle, and therefore the point number 2 would be that angle F equals angle D. And again, I can go proven because I've just shown why that happened. And now I've only got to give the third one. And I don't even have to prove it, so as I've said to you. So this is a beautiful example of it. I've used A1 and I've used F. I haven't used E1. So let's go E1. And I've used D and I've used A2. I haven't used M1. So I put it there and I'd say third angle of triangle. And therefore, by the way, before we move on, lots of teachers teach you not to put the third angle in, but I think it serves a purpose, because if it's there, when you come to write down your triangle in the right order, it's already there. You don't even have to think about it. So yes, it's not essential to write that third one down, but I would do it as a just good practice thing to do. So therefore, triangle AFE is similar to triangle ADM. And the reason is angle, angle, angle. Now, you'll see that the order I'm giving it in is not the same order as they asked it, but that doesn't matter because still position-wise they're the same. A is in the same position as A, E is in the same position as M, and F is in the same position as D. So we are fine with that. So right, we've proved our first part of the question. Hence, find. So hence means using what was above, the numerical value of AF to AD. So I want AF to FD. Now, as I said, you can write up all your ratios first of all and then sample them out. So let's do that because then you can see it. So you would say AF first 2 over first 2 equals last 2 over last 2 equals first and last over first and last. So I want AF, which is sitting over there, and I want FD, which is not sitting here at all, I don't think. No, it can't be FD. I must have copied something down incorrectly. Let me just go back here. AD. Oops, nearly a mistake. Sorry about that, guys. Just shows you how you've got to be so careful not to make mistakes like this. So that's AF over AD. So do I have AD in my little ratio? I think I do have. There it is. So now I've just got to decide what I already know. So let's go to the others. Do I know anything about FE and DM? And do I know anything about AE and AM? Now that is a good one, because what do we notice about AE? AE was the diameter, so the diameter could be seen as twice the radius, and AM is the radius. So I do know something about that, so I'm going to go AE over AM, and therefore AF over AD is equal to 2R over R. The radius cancels, and so we're going to get AF to AD is 2 to 1. Now I'm going to use that to my advantage, AF to AD. So if that's A, and AF would be 2A. That might be useful later on, so I'm just putting it in, and we can go from there. Okay, and of course we know that that's R and that's R. Right, let's see what the next question asks. The next question asks me to prove this similarity. Now this is where you'll find it so useful if they've said you prove this similar to this, because in effect, I shouldn't use the word cheat, you can almost cheat your answer in the sense that you know that the order's right, so you know which angles must be equal, and all you've got to do is go looking for why that is. So let's find ourselves a space to work at the drawing, because it's hard to not work at the drawing. Let's just get some space going here. See if there's any more room up here. Yes, there is. Most certainly there is. And one more, I think there's a little bit more up there. Take it away, and then we can use that space alongside. Okay, so what are we trying to do? We're proving CDB similar to triangle ADE. Okay, so notice I'm going to say this in triangle this and this, and we're ready to go. So let's go and see if we need to highlight in any way. I think we probably do. So let's use some spotty highlights. CDE, CDB. CDB is this guy here. And ADE, ADE is this guy here. Let's make a different kind of marking on that. Okay, so we're trying to show that those two triangles are similar. Now remember what I've said to you, we can effectively cheat. We know that because C and A are positioned in the same place, they have to be equal. Can you see why they would be equal? Well, hopefully you do. If we're using the points B and E, we have subtending an angle at A2 and we're subtending an angle at C, so it's angles in the same segment. So I can say C is equal to A2, angles in the same segment. Okay, this is a grade 11 theorem. If you've forgotten it, I'll just quickly put it over here. Looks like this, and basically it says that angle equals that angle. Right, and then they say that D must equal D. Well, that's also easy to see why. We know that these are vertically opposite. So the second thing I can say is that D4 is equal to D1 plus D2. Now, just while we're here, I want to mention, please don't ever do this. Okay, it's not acceptable notation. You write D1 plus D2, not D with a little subscript 1 plus 2. So never ever do that. It's not good notation. And after all, we want you to have good notation, so let's just stick to what works. And that would be vertically opposite angles. And then the third one is automatic, so we can say angle B equals angle E2. And there's a reason as well, but I'm just going to say third angle of triangle. And therefore, CDB is similar to triangle ADE. Reason angle, 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 or equiangular triangles is also fine. And you get the solution. Right, let's go to the next question. Now it says prove that AD squared is equal to CD times DE. So AD squared is CD times, let me just make sure I haven't written down the wrong thing, DE. Required to prove. Now notice they didn't say hence. Okay, they didn't say hence, they just said prove. So now remember what I said to you, we should try and find two triangles with AD in them. So if I go over there, AD will not be in two different triangles. But remember, I'd reminded you about that grade 11 theorem that said if this line is drawn and it's perpendicular to the chord, it's equal to this one. So we can say to ourselves that AD is equal to BD, and the reason for that is line from center, perp to chord. That's the grade 11 theorem. And so effectively, let's try and use this. So we're going to say it's first two over first two, last two over last two, and first and last over first and last. Let's see how many of these things we've got. Do we have an AD? Yes, we do. Do we have a BD? Yes. In actual fact, that's the same as saying AD. So we have two of those. Do we have CD and do we have DE? Yes, we do. So we can erase that one. And so we can say CD times DE is equal to AD times BD. But since BD equals AD, I could just as well go CD times DE equals AD squared. And as you can see, that is a really nice, neat little solution. And I think it was the last one on this question. Let me just check. Yes, it was. And that is a beautiful question. It's got so much in it. But you can see why I'm saying to you is if you can't prove one part, don't give up. So in other words, if we go back to the questions we had here, and that said prove this, and for whatever reason you couldn't, you could assume this and go down to that and still get those marks. And again here, if you couldn't prove that, you could assume that and go there. So there are always ways to get some marks on geometry, and that's why it's such a beautiful section. Right, let's try the next one. This is example 7, and it is quite a difficult question in the sense that it's lots of information, but I'm sure you'll be absolutely fine with it. It says KLM and KPQ are two secants. Now, what is a secant? Well, if we go back to our parts of a circle, we learned that if we drew like this, it was a chord. Starts at a point, ends at a point. If we draw like that, it is now a secant. It goes beyond the circumference of the circle. And it needn't go on both sides, just one side. So don't let that word scare you. It's just some terminology from our circle. So let's get rid of that so we can work. And let's go to the thing. They tell me there's a center O. Okay, hopefully they made it nice and big. They haven't, but we can do that, not a problem. And the radius is little r. Now, why they're telling me that, obviously little r is going to have something to do with the price of x. They've got it over there, but I can also put it here and here. And it's not a bad idea to do that immediately. They tell me that KL is 51 millimeters and LM is 24 millimeters. That's quite nice. But very nicely, they tell me that the ratio KP to little r is 9 to 4. Now, this is where I think it's an advantage to use that algebraic method I showed you earlier. Let's put in an A here, and let's go along to it. So KP is going to be 9A, and little r is 4A. So I can call this 4A, and I can call this one 4A, and I can call this one 4A. It just is easier because now I've only got one variable I'm working with, so I can sort of forget for now about these r's. Right, let's read on. Prove that KPL, so in triangle KPL, and KMQ are similar. Now remember the cheat I told you about? This could be very useful. Let's highlight our triangles first of all. So KPL, let's put little tritracks on that. And KMQ is the big guy. So let's highlight him completely. So KQM. So having highlighted, you can see clearly that we have a shared angle, which is really nice to know. So let's go along to it and let's start working. I think I'm going to work in blue. So the first thing I can definitely say without any trouble is angle K equals angle K. It's a common angle. Right, now P equals M. P equals M. Why would that be? Well, hopefully you're thinking back to your grade 11 theorems, and that's why again I'm nagging you to think of them in terms of diagrams rather than something else. Do you remember the exterior angle of a cyclic quad equals the interior opposite? The exterior angle of a cyclic quad equals the interior opposite. So we can say that P equals QML, if you like, and the reason would be exterior angle of a cyclic quad. And then the third is automatic. The third one is that L equals Q. And again, if you looked at it, you'd see why it's again that exterior angle of a cyclic quad, but we don't have to do it. We just say third angle of triangle. Therefore, triangle KPL is similar to triangle KMQ, and you can go angle, 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 or you can go equiangular triangles, just to show you in case your teachers have been using that notation exactly the same. Right, so we've got the first part proved. Now it says show with all, notice the highlights, steps, and reasons that little r is equal to 20 millimeters. So now they want me to prove that r is 20 millimeters. I'm just going to take this drawing off over here So it actually had nothing really to do with that. And let's get ourselves another color pen so we can distinguish with what we're doing. Let's go there. Right, so with all steps, I must show what little r is equal to 20. Now, looking at it, I've just proved a similarity. Maybe that has got something to do with it. So let's write it down. Kp, the first two, over the first two km, equals PL, the last two, over the last two MQ, the first and last over the first and last. Okay, so if I look at this, Kp is 9a. Km is 24 plus 51, so it's 75. PL I don't know anything about. MQ I know nothing about. KL I know is 51. And KQ is that whole length, which will be 9 plus 4 plus 4, so it will be 17a. Now, what is nice to see is that 17, or rather 51, is a multiple of 17. So that means before I even start, I'm going to say 17 goes into there once and into there 3 times. And that will just make my arithmetic much easier, because to work with 17s and 51s is never fun. So right, if we're over here, we can now cross multiply. So I have 9a squared equals 3 times 75. And if I look over here, and I'm going to bring it over here so we can work with it, a squared will equal 3 times 75 over 9. Of course, you can use your calculator, but I'm trying to encourage you to think a bit. And if you look over here, that's going to go divide into the 25 times, so I get a squared is 25. That means that a is either plus or minus 5, but we are dealing with a length, and a, being a length, cannot be negative. So I can safely just say a is 5. Now, how does that help me with my story? Well, if I go back to this drawing over here now, and I erase that 9 and I put in a 5 for a, well, then my 9a would be 45. And if I erase this over here, in fact, I'm going to take that off as well, it's 4a. 4 times 5 is 20, and that's very good news. Now, since r equals 4a, according to my theories just now, and by the way, what I should have done in the beginning of this question is I should have said, let Kp be 9a and little r equal 4a. Although I did it on the drawing, it's a good idea to actually say it in your work. So right, over here we go, and we now say therefore r is equal to 20, and it's millimeters. Right, so that would bring the solution to this with all your steps. You can see it clearly. And so yes, r is equal to 20 millimeters. Thanks for joining us with the Euclidean Geometry, and as you can see, I'm sure it's something that's very manageable, so all the best and good luck.